If you remember, our problem was whether we have a kind of a mold to cast a given polyhedral shape, polyhedral object. This is an example, for instance. It has many faces. All the faces are planar, and obviously if they are planar, then the shape should be convex sometimes, but it may also be concave, depending on the complexity of the shape. If it's convex, then it's much easier to find kind of a single mold for it. But if it's concave, then you may need to use at least two of the molds, let's say, on top of each other. And sometimes, if the part is more complicated, you may need to use 3 parts, 4 parts. So depending on the complexity, also the complexity of the mold will increase. And we will try to find whether there is such a mold or not for the given shape. This is our problem, and for that problem, we will propose using linear programming. So these were our simple assumptions, and we said that we want to have just a single translation in the given direction. It might be just in pure z direction or tilted z direction, but the thing is that we need to have non-zero or positive, let's say, z values. So we had some definitions. We have a term called top facet, and it's the facet which has actually no contact with the mold. This is the facet of the part of the polyhedral object, the top facet, and the other facets are called as ordinary facets. So this is the top one, and it has no contact with the side surface of the mold or any surface of the mold. It's open to air, and with the help of it, we will remove our casted product from the given mold. So I will now, discuss this one. This is a cross-sectional view. This is our polyhedral shape, as you see, and it has a top facet here and some ordinary faces. And these ordinary faces are shown with the letter F. And we also have corresponding faces on the mold side, and these are represented as F bar. So we have two options. If you want, if this part is actually castable, then that means you can remove this part by sliding along a facet or moving away from a facet. For instance, if you move it in that direction, it's obviously sliding along this facet, but it's moving away from the bottom facet. And we said that in the formal, let's say, explanations, algorithms, we need to have an angle definition so that everyone is on the same side. And if you look at our angle definition, the thing is that once you have two vectors, and if we call an angle between these two vectors, the angle will be the one which has a smaller value than the other one. So we will not be considering the outer angle. This angle is not important for us. And the important one is the smaller angle, okay? And we will be using it a lot. And we had a bit more complicated shape, and if you remember, we discussed on this shape, on this slide, and come up with the assumption that, or requirement that, if the given polyhedral shape is, the given mold is suitable for the casting of this polyhedral shape, then its faces, these are the facets of the mold, if you remember, this is ordinary faces, and corresponding facet on the mold side, they should have at least 90-degree or more angles with the output normal of our ordinary facets. This is our requirement. If it's less than that, then that means we cannot do the casting. So this is actually the summary of the discussion in the previous slide. The polyhedron P can be removed from its mold by a translation in direction given d, if and only if this direction vector makes an angle of at least 90 degrees with the output normal of all the ordinary faces of P. So if it has a problem with any of the faces, then we cannot say that it is castable. For instance, if there are, let's say, 6 faces and 5 of them has angles more than 90 degrees or equal to 90 degrees, but if there is only one facet having an angle of, let's say, 85, then it's not possible. You cannot say that the given mold is the correct one. So you should find another option, or you may state simply that this part is not castable with a single mold. Another simple issue is that this is our theorem, and here it says that if you have small, let's say, translations, so if you come up with this, let's say, sentence, here since it says that you can only make small translations, but if you prove that your part can be moved in this direction with a little amount, then that means we can move it in that direction completely to infinity. This is another, let's say, an extra comment on the theorem. So the thing is that if the given angle is, all the angles are fine with our requirement, then we should be able to find a specific direction or some, let's say, number of directions. And this vectors actually would represent kind of points on the z equals to 1 plane. So this is the simple z equals to 1 plane, as you see here. And these are some direction vectors. This, right, this one is d1, and this is another direction vector, d2. So as you see, if you have such a plane, z equals to 1 plane, then the intersection of these vectors with the plane will be just simple points. So if you can somehow state that this point is in your feasible region, we can simply say that you can remove your casted product in that direction. So our problem will be simplified into this. We will be trying to find whether the given points are in the feasible region or not. Now let's focus on the normals of our ordinary faces, and we'll be using the vector eta for that. This is a normal vector of the ordinary faces. What were the ordinary faces? They were represented with F, if you remember. So these are ordinary faces, and we will be considering the normals of all these ordinary faces, but not the top faces, since it's always open to air. We don't have any issues with that. And the direction vectors, as we discussed in the previous slide, has a component of 1 for the z-axis. And if you remember our theorem, first lemma, we said that we should have at least 90 degrees or more between these two vectors, the normals of the ordinary faces and the direction vector. So how can we check it? If you simply take the dot product of these two vectors, and if the result is non-positive, then yes, we can say that the angle between these two vectors is more than 90 degrees. If it's equal to 0, we will say that the angle between these two vectors, the direction vector and the normal vector of the ordinary face, it is 90 degrees if the dot product is 0. So this is our dot product results. We are multiplying the x components together, y components together, and z components together. Since it's 1, so we simply have an 1 here, which is not written for simplicity. Any questions, guys, up to now? Okay, let's go on. So what are these vectors or the inequalities are representing? It's simply a kind of an half plane on the z equal to 1 plane. So we have a kind of an plane. This is z equals to 1. This is our plane. And if you actually work on this inequality, you will come up with an, let's say, such a line. And that inequality will be representing maybe this left-hand side of this, let's say, line, okay? So this is the line, and this is our z value, and depending on it, we will have some different regions on this plane. And as you see, this whole plane is divided into two. That's why we call it as a half plane. With the help of these inequalities, we are dividing the z equals to 1 plane into 2 halves. And so how many inequalities are we going to have? Can anyone tell me how many of them we should have? So the number of inequalities depend on which parameters? Are you with me, guys? Okay, assume that now this is your quiz. Please send me your answers in the chat area in private, let's say, answers. Send your answers privately to me, okay? You have just a minute. So the number of inequalities depend on which parameters. Your time is started. Okay, send it as a private message. Your last seconds. So how many inequalities are we going to have? It should depend on some value, right? We have a polyhedron, and we want to find a kind of a mold for it. And the question is, how many inequalities should we have for the given polyhedron? You may change your answers if you have new, but your last, let's say, 20 seconds. Okay, time is over. Please don't send any more answers. So can anyone unmute themselves and tell us the answer, or we may start a discussion on it. So let me draw the cross-sectional view Oops. Yes. See, once again, we have such a cross section of the polyhedron. Okay, this is our polyhedron P, and it has, as you see, a top facet. And we have some ordinary faces, right? This is F, this is F. And we said that we are trying to find an possible orientation in which actually we can take our part out of this mold. And we said that we have such half planes. And as you see, these half planes depends on which parameters? What are these eta? These are the normal vectors of the ordinary facets. So it depends, the number of inequalities simply depends on the number of ordinary faces. Okay, this is the answer, simply F. Any comments, questions, guys?
Hocam, what is the difference between facet and face? I don't understand that.
The same, the face is more, the larger one, the facet is just one portion of this polyhedron. I don't know whether you can see this one. This is a facet, facet, facet. And face is a more general term, and facet is the thing actually we use in geometry. That's why we prefer to use it here, but not much difference.
Thank you.
Okay, no comments. So the thing is that if you have one half plane for each, let's say, ordinary faces, then what we are going to have, you have a more complicated, let's say, region. I am drawing a top view of z equals to 1 plane. Okay, this is z equals to 1. And if you have many, let's say, ordinary facets, and if this is one region, let's say, this might be another half plane. In that case, these will be the valid regions. You may have another half plane here, and in that case, we might have this upper side as a valid region. And as you see, we have an intersection in this region. This is the intersection of all the half planes. And if you remember in the previous slide, we said that these direction vectors are representing just simple dots, simple points on the z equals to 1 plane, right? So if your direction vector, if the intersection of your direction vector with the z equals to plane is in this region, in this closed region, then, and on the other hand, if you also point out that this is a feasible region, if this is a feasible region, and if you find your point in that region, you can simply say that, yes, we can do the casting and remove your part in that given direction. So this is what we are going to do. We will do some computation, try to find this region, whether we have such a feasible region or not. And if you find that region, you are quite fine. And if you're furthermore, if your direction vector is intersecting this z equals to 1 plane in that region, then you can simply say that, yes, we can remove our part in that given direction. Any questions, guys? This is actually the summary of what we are going to do. So obviously, if we have no intersection of these half planes, then we can simply say that there is no possible mold which can be used to cast this given polyhedron. So here you see, for instance, an example. This is z equals to one plane once again, and we have some half planes. By the way, these black lines are representing the lines, and this if this gray region is on this side, then that means this is a feasible region for that given half plane. And this is not valid. This side, this bottom side, is not okay for the given inequality. And as you see, we have how many? 1, 2, 3, 4 half planes, and that is the intersection of the 4 half planes. This has no direct contact, but if you look at here, this is the feasible region for that upper, let's say, half plane. So this is the feasible region, and if you have an direction vector intersecting this plane in this region, then we can say that it's okay. So there is another question. So if the polyhedron which is to be manufactured has n facets, like this one here, if it has n facets, then the planar problem has at most n minus half planes. Why is that? This is not a quiz, by the way, just a question. Why we have 1 minus half planes? There's a simple answer. Why we have 1 less half planes than the number of facets? No, Mithat, not correct. Yes, Rahman, you are correct. We don't consider the top facets since it's always open there, and we don't have any inequality for the given top facet. We can only write inequalities for the ordinary faces which are inside the mold. So that's why simply we have n minus 1 half planes. And we will be actually showing that this planar problem can be solved in expected linear time. So this is the first time I think we come up with a different time complexity. This is expected linear time. So it means that for most of the time, it will be done in linear time, but depending on your arrangements, it may take more time. So we are going to actually, at the end of this chapter, we will come up with such a solution. And our algorithm will be computing this, let's say, problem, this solution in expected linear time. And simply, this is actually the brute force method. So if you don't have any specific algorithm in mind, then what you're going to do, you may simply take your shape, select one of the faces as the top facet, and then check all the angles of the other faces, right? And if this is wrong, then you may orient it in different direction, do the same for all the ordinary faces once again, and you should be doing it for the number of faces. And this is the brute force method, but obviously we are going to find some better algorithms which will take less time. So this is actually the brute force method. If you have a polyhedron P with n faces, then in quadratic time, quadratic expected time, and using linear storage, it can be decided whether your polyhedron is castable or not. And if it's a castable, obviously, you can tell the user or the people in which directions they should be actually removing their part from the mold. But in summary, this is the thing, and you can, in brute force approach, you can do it in quadratic time. But we'll try to find some methods which will be computing this problem in expected linear time. So now let's have some formal definitions. We said that on the plane, there are some half planes, right? On the z equals to 1 plane, we have half planes, and this is actually our set of half planes starting from 1 to n, which means that we have n number of half planes. And these are represented with this inequality, as you know. So our problem is actually find the set of points in this plane on this x, y, let's say set, which will satisfy all the constraints here. So our aim is to find a region of x and y values, and the thing is that they should all satisfy the given sets, the given constraints here. And obviously we know that this region will be a convex region since we are intersecting always the half planes. Since we always have such linear lines, we can always have convex regions. We can't have actually kind of an, let's say, concave region. This is not possible. We always have convex regions. Any questions, guys? And the thing is that this convex region, this convex polygonal region can be bounded at most n number of edges. Since if you have, let's say, 3 of them, and that region will be bounded at most with 3 half planes. This is the maximum. For instance, you may have another half plane here, like this one. But as you see, the region, if this is a valid part, valid half plane, and this will not change. And this time, as you see, it will be 1 less than the number of half planes. This one is not important since it's not intersecting with the other regions. So we can say that at most, the number of edges of this polygonal region can be n. And sometimes it might be n-1 and -2, depending on the arrangement of your planes, but this is the maximum value. So you see some possible intersections. We have a closed region here. This is unbounded, as you see, in all directions here. This is another unbounded region. And here it's a bit different. We have a single solution. And what about this one? We have, as you see, no intersection, so this is not feasible. If you come up with such a polygon, such a region, or you don't have a region actually, you can simply say that the part is not castable with a single mold. So let's have a look at our algorithm, what we are going to do. So as you see, the name of the algorithm is intersect half planes. Since we have simplified the problem into the intersection of half planes. In the beginning, our problem was to find whether the given part is castable or not. But right now, we have done some modifications, and now our problem is to find the intersection of half planes. So if you can easily find whether these half planes are intersecting or not, and find that intersecting region, then you will be done. Since the rest is not that complicated, if you have such a region, then you can tell the user that if they have any direction vectors intersecting with this region, then they will be fine. So let's have a look at the details. It's not that complicated, but this one is a bit complicated. We will spend more time on it, but I will go through the whole algorithm first and then start discussing the last one. So what is our input? Input is simply the set of half planes on the plane on the z equals to 1 plane again. And we will be trying to find the intersection of all these half planes. So simply the output is the intersection of all the half planes in this given set. So how we start? We check if the cardinality of the given set is equal to 1. If it's equal to 1, then we don't need to do anything, since that means we have a single half plane. then the output will simply be equal to C. But if the cardinality or if the member of the set has more than one values, then what we are going to do, we will be trying to divide this set of, let's say, constraints into two groups. This time we will have H1 and H2. So this is if, let's say, we have, assume that we have 7 half planes. Then what will be the value of H1? That will be 4, and H2 will be 3. Since we are using sailing and floor functions here, so the first one will have 4, and the second one will have 3 half planes. Then what we do, we compute the intersection of these half planes first for the H1, which is 4, and then we do the computation for C2, for H2. And their results will be stored into C1 and C2 respectively, right? But the thing is that, let's say, let's focus on the first case here, H1. Can everyone comment on this algorithm? We have a nice property, and what is that? Did you realize it?
It's a recursive algorithm.
Yeah, this is the main, let's say, issue of this algorithm is calling itself, right? The name of the algorithm was intersect half planes, and now we are calling the same function inside that function. So this is a recursive function, recursive algorithm. So what we are going to do, this one is 4. So if you run the same algorithm, again, inside this part, our constraints will be divided into, once again, 2 parts. This will be, let's say, H11, name it like H11, and this will be H12. So we will be dividing these until you have always just a single element, and then what you are going to do at the end of all these, let's say, sub-recursive points, you will be joining these 2 parts. So we can simply say that actually the algorithm is not that complicated. What is it doing is that it's always joining simple half planes together. For instance, at the beginning of this one, if you have 7 half planes, then initially it will be trying to take the intersection of, let's say, 2 half planes. And then what's going to do after you have this region, then you'll join them together once again with other, let's say, computations. So let's focus on here. We intersect 2 half planes. On the right-hand side, we all have also done the same. We have taken the intersection of 2 half planes. And then what we do, we take the intersection of these 2 separate parts. So now 4 half planes are intersected. And also on the other side, we should have 3 half planes intersected. And later, we will again join these together, intersect these 2 regions together, and have the final result. So at some point, actually, we might have such regions. Let me try to illustrate it. You may have such a C1, let's say. This might be C1, okay? And let me use a different color. Oops. I'm sorry for that. Let me quickly draw it. This is C1. Let's change the colors. So this was the red one is C1, and you might have another one, and that might be C2. So in the C, what you are going to do, you will join these 2 together. Join these 2 parts together. So now let's have kind of black. So that will be the C. Oops, is it white? Why is that? Oops, I selected white. I'm sorry. So that will be the intersection of the C1 and C2. So the most important part is, the most complicated part is the last algorithm, intersection of these two convex regions, how we are going to intersect these two regions together and have a feasible one. So now our problem is simplified to the intersection of two convex regions. So once you have these convex regions and have complete this intersection properly, then that means you are done and you can simply state whether your part is castable or not. Any questions, guys? So this is one actually spend some time on it. So these are two half planes, C1 and C2. You see an example. Sometimes they will have such intersection points like V here, and we have an H1 of, let's say, C1 and H2 of C2. So we will do some computation and try to find these intersection points. And these C1 and C2 can have at most m/2 plus 1 half planes. Why is that? And their number of edges can be at most, again, the same value, n/2 plus 1. Why do you think is that? Why we have such a limitation? If you remember, in the algorithm, we were dividing these regions into two halves. So at most, assume that if you have n number of half planes, then at most this one might have n/2 plus 1 half planes. This is the maximum we can have. And now we didn't discuss, but in literature we have some algorithms which can compute this intersection of let's say two convex regions in n plus k times logarithm of n. We will take it as granted. I'm not going to spend on time for the derivation of this, but we can assume that there are such algorithms and they can find this intersection in kind of linear arithmetic time. And once you take the intersection of these two half planes, you may at most have n number of edges, which is equal to our number of half planes. Again, the complexity obviously will be similar to this one. And since, as I mentioned, we take that time complexity as granted, I don't want to spend time for it. The total running time will be similar to that. We have, since we are dividing these regions always into halves, that's why we are multiplying with another logarithm of n, and that will be n times, as you see, logarithm square times square of n. But this is with time consuming, close to quadratic, not exactly equal to quadratic, but close to that. So we are trying to find a better algorithm which has less time complexity than this one. And we know that the intersection regions are always 2D, right? You see here, we have C1 and C2, and this is the whole, we may say that this is the whole intersection, convex region, and it sometimes have left boundaries and right boundaries. And you see that these are the half planes defined starting from H1 to H5. And if this is the intersection point, then the ones on the left-hand side of it will be the left boundary, H3, H4, and H5. And the ones on the right will be considered as the right boundary. And in the algorithm, they are stored into some separate lists. And then we'll be trying to find these intersection points. And later, once these computations are over, we will say that this is the resulting region is the intersection of this half planes.